Hi, Chris. Can you hear us?
Yeah, I can hear you.
Okay.
Yeah.
Okay, welcome back, everybody. We're about to start our second session, which is going to run from 11:15 until 12:30. At which point we can have lunch. This is concerning core collapse supernova and supernova remnant modeling. Our first talk is Chris Pryor from Los Alamos. It's an invited talk. It will be 25 minutes plus 5 minutes for questions. Chris, you're welcome to begin.
Thanks a lot, and thank you for inviting me to give this talk. Usually I am surprised and worried that you made a poor decision, but that's how it is. You made the choice. I wanted to talk a little bit about how all of the models, there's lots of diagnostics on understanding the supernova engine, and I want to talk a little bit about that. Before I start, I wanted to point out that Pat Slane's in the audience, and whenever Pat Slane, I see him at a meeting, I always look at his T-shirt. So you should look at his T-shirt and see what it says. And in honor of Pat Slane, I also have a science nerd T-shirt. And if you can't read it, that's how I roll, is what it says. So always look at Pat Slane's T-shirts. He has good ones. And I will go on with my talk. So what I wanted to talk about is, and I'm going to start wandering around. So I'm going to turn off my video so that you don't see me wandering around my house. When we look at supernova, there's just a wealth of information and a wealth of reasons why we want to study supernova. I think it is worth us to understand this broad picture and actually keep on selling it. I know the decadal review was good for time domain astronomy and multi-messenger astronomy, which supernova are, but it's good to keep on putting that message forward because there's so much that we can learn both in physics and in how astronomy affects from things like supernova and astrophysical transients. So we have all these things that supernova affect. We need to understand the engine, and there's more than one engine proposed. There's an engine where you have core collapse, neutrinos, convection driving the explosion, but NOM is here, so I would be remiss in saying that you can also get jets from disks, and when I think NOM and I agree on what we mean by jets, because it doesn't mean that it has to be an MHD driven relativistic jet when you're doing it. It could be you form a disk around the compact remnant, and that disk wind blows a very bimodal explosion. So there's different engines like this. You can also have magnetars. We want to understand what is the dominant engine for supernova that we observe. The other engines will exist. So there's for those of you that haven't heard this, it was first time I saw it mentioned in astrophysics was by Kip Thorne and Anna Zitkoff, where they were trying to justify Thorne-Zitkoff objects, and they did a quote from The Once and Future King, which is a book about King Arthur. But in this particular story, they had King Arthur getting turned into different animals, and then the animals were representing different political viewpoints. And it turns out that the one that they quoted was from when King Arthur was turned into an ant, and at the front of the ant colony, it said something like, and I'm not going to get the quote exactly, that which is not forbidden is mandatory. So that which is not strictly forbidden is mandatory. And the fact of the matter is, when we have different engines, if we can say that the physics allows them to exist, nature will find a way to produce them. The question is, how often does nature produce them? How many explosions are more these bimodal outflows from jets or disk winds, and how many are from the convective engine? What are the characteristics of the convective engine, and how do we constrain all this? So how do we actually know The problem is that the most direct diagnostics of what's going down deep in there are things like gravitational waves and neutrinos, and those are hard to obtain. They're just rare. So we have to end up using other diagnostics, and the other diagnostics tend to be indirect, which means that we can't just get away with doing the supernova engine calculations. We have to add other calculations on top to get to those diagnostics. And so let me kind of give you a picture of the kind of broad vision I have when I think of all the diagnostics for this to try to probe what's going on in this engine. And unfortunately, it requires a lot of us working together. There's this tendency for people not, especially theorists, we don't play well together. We try to do the calculation all the way through with a single code, and we're happy with that. I would argue that we need to think more broadly on how we do this science. And let me just go over some of the issues that we're dealing with. We have the progenitor. We want to understand its mass loss. We want to understand the convection just before collapse. We want to understand the convection in the outer layers also affects the explosion, and I'll talk a little bit about that as well. So we need to have good models of the progenitor, not just in 1D, but also multi-D effects. In the engine, the engine can tie to things like gravitational waves and neutrinos, like I said, so that's we can make some direct predictions. But for the most part, we're going to have to move beyond just what can the engine predict to get to diagnostics that we are more plentiful. The engine requires a huge amount of physics in nuclear physics, so dense nuclear matter, neutrino physics, general relativity in cases, magnetohydrodynamics, turbulence, nuclear reactions. So it requires a lot of physics to be added, and the engine folk often work closely with these physicists to try to implement better physics. But there's not really, we're getting better and better at these models, but they're not at the level that we're not at the level that we're going to give quantitative solutions that we know are true. And I'm going to tell two stories coming from the engine perspective that kind of shaped my viewpoint on this. One was when I was doing my thesis, I was looking at fallback onto neutron stars, and I was reading papers by Roger Chevalier, and I thought, okay, those analytic papers, they're just analytics. I'm going to do so much better by doing these simulations. So I did all these simulations, and I started to compare to his analytic solutions. And when I compared the salient points of my simulations to his analytic derivations, he was spot on. And those analytic derivations gave me an understanding of what my simulations were doing. And so the lesson I learned from that is we can't just run a calculation, get a result, and say, there. We need to actually tie it with theoretical understanding. So this kind of applied problem where we're trying to understand all these features together is not so different than the main problems that we solve for national security here at Los Alamos. And Dimitri Mihalis came to Los Alamos, and his first assessment of the labs was, because we were doing the same kind of thing where we were running calculations, hitting return, getting a result, and that's what we were doing. And he said, you need to start using that thing between your ears. You need to start thinking about what your simulations are telling you, not just what is the answer it gives, but what are you learning about the physics from it? And things like the analytic solutions actually play a big role there. The other lesson I learned was at a KATT workshop, and I'm not going to mention the scientist that was giving the talk, but Brian Schmidt stood up at the end of the talk and said, why should I believe you this time? And that's where, one of the things we're going to have to do as engine people or in any of these phases is understand what's going on well enough in our calculation so that we know what do we believe and what do we not believe. So in some cases, this is asking a theorist to do uncertainty quantification. I know we don't like to do that, but that is, when we're doing an applied problem like this, we need to understand what do we know, what do we not know, how does it all fit together, what are we learning from the calculations. You take that, you characterize explosion properties, you then follow it out even further. And let me tell you, this community, I know I'm kind of preaching to the choir because we already do this. We've already seen some talks doing this. So, where people are taking the results of one calculation and seeing what they can learn from them, seeing how it ties to observations. This is a community that knows this. Why I'm saying going through this talk is this community needs to be proud of that and actually sell that. So this community does bring everyone together. I think this is the way to really sell these kinds of calculations. So you then want to run the explosion through the star. That will help you get other nucleosynthetic yields. So that things like titanium-44, there's stuff that's made right in the center, and that's depends on the engine. As you move further out, things like iron-60, that's made further out. So you need to actually study how does the explosion propagate through, how much of the helium shell is going to get turned into iron-60. That depends on the nature of the explosion and these asymmetries. So again, you can model that, and you can go all the way through getting nucleosynthetic yields. After you get fallback, you'll know something about the compact remnants, compact remnant masses, compact remnant spins. You can study shock breakout, and I'm going to talk more about shock breakout because I think it's one of those fields that we will get more data and we can learn. It's another probe that we haven't used as well as we could. There's lots of data on light curves and spectra from the light curves. There's data from gamma rays, but that requires even a further calculation. You typically aren't going to use your rad hydro code to calculate light curves because at some point you can reduce how much you depend on hydrodynamics and shock heating and just do pure transport. But beware of that because we're seeing more and more in these supernova light curves that shock heating can play a role in what the light curve looks like. So you can't just do a pure transport calculation. And just so you all know, most of the light curve calculations do assume just pure transport. So they do a homologous outflow and they do the transport. So gamma rays, and then what this meeting is all about is the ejector remnants, right? So those observations. And all of these fit together and all of these need to be tied together. The physics in each of these can change. So you go from needing to know the nuclear physics to radiation hydrodynamics. Turbulence is involved in a lot of these. You need to understand cosmic ray production, the non-LTE effects that we've already had some discussion on. You need to understand atomic physics, radiation transport at a detailed level. So there's a lot of physics that goes into this as well. So this is really a nice grand challenge problem if I want to study the engine, how do I get all the diagnostics that I want to use to study this? So this is the main point of my talk. If you turn off now, that's fine. Now I'm just going to go and give some examples of studies that we're doing, but they don't fit all together yet, right? So we do. What would be nice is to get, everyone, people figuring out how are we going to fit all these pieces together to tie to all these diagnostics. So I'm going to go quickly through this. There's the direct probes are neutrinos, gravitational waves. What's really interesting, and unfortunately the paper's not out yet. I had seen a copy of it, but they haven't sent it out. I think we're still learning from the neutrinos. So there's this Lee et al. Paper 2021 showing the potential for neutrinos in the future with hyper-K. A nearby supernova will give us enough data to start probing other aspects of the supernova explosion. But I've seen a paper that in the draft phase that's going to show us that even with what we have from 1987A, there's more science we can do than we thought we could. So this is a field that's still active. There's still science we can learn. Gravitational waves, I'm hoping Sarah's going to go in more detail on all the interesting science that we can do with gravitational waves. I think these tie together. Looking at the gravitational waves and neutrinos will teach us a lot of science. But these direct probes are rare, right? So we still are going to have to rely on other data. So one of the things that I've gotten excited about recently has been shock breakout. This is what happens as the supernova shock goes through the star and breaks out of the star, and it's that first bit of burst of emission. And the simplest model is a nice spherical explosion. You assume that the forward shock is where all the heating is, so you're just looking at that burst of photons from the forward shock as it becomes optically thin, and those photons are released. Unfortunately, the problem is way more complex than that. The shock itself is not symmetric. So that changes the emission you see. So there's a nice paper by Chris Irwin out in 2021 on this. There's the shocks as the shock is moving through the star, and I'm hoping Rick Hicks talks about this. But there's also a nice paper by Tsang et al. 2022 looking at this kind of the shock moving through an inhomogeneous medium through the star. So there's that feature. There's shocks when you have once the shock bursts out of the star, it's going to shock against inhomogeneities in the wind, and that's this figure on the bottom left, where we did some initial calculations for a Wolf-Rayet star explosion, and we're looking at how does this tie to what can we do from the observational point of view? Can we go and look at see evidence for these shocks? And there's this assumption that it only happens in that you only get to see it in that initial burst of photons, and it's like 2008D, 1,000 seconds long, and it has to be certain stars, or you don't see much in the X-ray or UV. Interestingly enough, XMM there was a nice study with XMM by Alpen Larson in 2020, where they actually found not just for Wolf-Rayet stars and so these more compact stars, but also for red supergiants, there's evidence of X-ray emission at that shock breakout stage. Whether you believe they're events or not, I think it's tantalizing to say that you can actually get some X-rays. And the reason you would get these X-rays even in red supergiants is because there's shock heating. That it's not that simple picture of a nice spherical shock going through a nice spherical star and spherical circumstellar medium. So there's lots of information you can get at. If you can see some of these inhomogeneities in the later time UV. So even when you're a few days out, you can still see evidence of this kind of shock heating that's gone on as the star was that the blast was moving through the star in the wind. So that's Amanda Bayless has done some work on that in 2022. So there's a lot of interesting results happening in this field. This is probably the last time I get to show this slide, because on Thursday they're going to select mid-X missions, and so then I can't be happy about Psydex anymore when it doesn't get selected. But on Thursday, I think we will know what kind of missions are getting to phase A in the current mid-X round, and I suspect something is going to be exciting getting to the phase A stage. Something is going to be an exciting potential for studying astrophysical transients. But the Psydex mission is a mission designed to observe the shock breakout. It not only gets the ultraviolet, it gets the X-ray, it gets spectra. It'll start to help constrain all these uncertainties we have in the shock breakout arena. Even if that isn't supported, the Ultrasat mission is going up. It's going to get UV. It will get these observations. It'll start to build up our database of shock breakout. So I think in the worst case scenario, we have Ultrasat. In the best case scenario, we'll have Ultrasat, and 10, 15 years later, we'll have Psydex. So there's, I think, a lot of interesting results that happen here. But let me say how this ties together with other physics disciplines. An example of this is that we're actually studying inhomogeneous rad flow in the laboratory. So there's experiments being developed that study the propagation of radiation, a radiation front through a shock and a blast wave through a target that has inhomogeneities in it. So this is not just we're doing it on our own. We're astrophysicists. We're all on our own on this. There's physicists that can help us study this field, and experimentalists as well. So this is the plot in the middle is the design of a experiment where we have a hole rum, where we shoot lasers in the hole rum, heat up that hole rum, and it sends a radiation front into a target. This target has placed inhomogeneities in it, and we're studying the interaction of that flow with these inhomogeneities. And the interesting feature here, so this is my job, my main job at Los Alamos is I model laboratory experiments. So I try to understand what's going on in laboratory experiments. I did not come up with this experiment, but I realized, oh my goodness, this is going to help us on our astrophysics. I was modeling the radiation front through this inhomogeneous rad flow, and the experiment itself is about a centimeter in size, so it's very tiny. But all I had to do to model then the shock radiation front going through a Wolf-Rayet wind was to change a few buttons, increase the size by about 10 to the 11 times, and I was starting to model the radiation transport through an inhomogeneous medium there. And the point I'm trying to make is that the physics starts to be the same. It may look very different because one is 1 centimeter in size, the other is 10 to 11 centimeters in size, but it's the same physics, and we can actually leverage physics done by these other disciplines. The turbulence community has a lot of ways of dealing with say calculations that we're under-resolved on, and you need to have some kind of subgrid model. Astrophysics has been a little bit slow in, I guess, embracing these Reynolds average Navier-Stokes solutions for the subgrid turbulence that you're not including, but I think there is potential for us there to leverage that physics. So it's not just we have to work together as astrophysicists, but we're going to also be working a lot with other physicists. And this is something that the remnant community already knows, because for atomic physics, non-LTE physics, they've been working with atomic physicists for ages. We've been looking at light curves and spectra, so I'm showing there's lots of groups working on this. So I'm showing some figures from some of my recent work, or people that I work with, their recent work. But this is really, we have lots of people studying these kinds of effects. So one of the things we wanted to do is what happens if you have this extensive mixing, you have asymmetries in your explosion, you have extensive mixing, how does it affect the light curves in the UV, optical IR bands? How does it affect the light curves? And the fact of the matter is, light curves may not be the best probe of this until you get to the late times and you start entering that nebular phase. And that's where I was really excited about Bart's talk. As you get to later times, you hit the nebular phase. You have to worry about all that non-LTE physics, but that's where you start to see these the effects of mixing. And so on the left here is a couple band light curves. So I have G band. I have the bolometric, and then a couple other bands, W1 band, U, V, R, K. So I'm going through ultraviolet all the way to K band. And I'm showing that the solid line is with minimum mixing, the dashed line is with extensive mixing, and you can kind of see how it affects the light curves. And so if you just look at it in the earliest times when you're in that plateau phase of a supernova, it's going to be hard to distinguish. But as you look to late times, it does make a difference in how the light curve behaves. And this is just where's the material ending up, where's the radioactive nickel playing a role. So radioactive nickel doesn't play a huge role in type 2 supernova light curves at early times, but as you get to later times, it'll alter the emission. And on top of that was Bart's talk showed you how it will also affect the line features. So you can start saying line features. Gamma rays provide a really strong constraint on the amount of mixing, and it's the same reason why we got it. Gamma rays pushed us to look for mixing from 1987A. The appearance and of the gamma rays depends sensitively on how much mixing you have. So the time of appearance depends on that. And so you can look at the gamma rays and say, okay, the gamma rays came out early. That means we had pretty good mixing of radioactive isotopes like nickel 56. A thing to take, so there's been several missions that are proposed in the gamma ray to do this, again, in this mid-X round. So there's lots of missions being proposed. Since only 2 probably will get selected for phase A study, it's unlikely we're going to get everything we want, but there are some gamma ray missions like LOX being proposed that would be really ideally suited for this kind of observation. Compact remnants is another way we could study supernova mixing. And one of the big questions we have on supernova mixing is how quickly does the mixing grow? How quickly does the convection grow? This depends. There's some nice papers by Carl Fields and Sean Couch studying what happens if you, and others, what happens if you have strong silicon burning just before collapse? How does that affect the growth of the convection? It provides a seed that helps start that convection and get it growing earlier. So the growth of the convection is really important. Understand that when we do our calculations, we're not really resolving the convection very well. So we can be getting the growth wrong. and that's something that we need to keep on improving our physics on. But if we have strong seeds, they'll overcome the lack of resolution and probably get us through and get convection growing fast enough. But there is you can do analytic studies where you say, well, if the convection goes quicker and drives an explosion faster, what does that do for the compact remnant mass? And we did that study recently, and we found that you can fill in that mass gap between what's the most massive neutron star and where's the first black hole, depending on how the mixing, the growth of the mixing. So it's an indirect probe. It's way uncertain, so I wouldn't take this with a grain of salt if we get a nice fill-in of the that mass gap from observations from, say, LIGO. You're not going to then be able to say, and that means the growth time is this, but it does give us a handle on what's happening with the growth time in the mixing. And this is also an example of taking advantage of not just using what we standardly use for subgrid models for convection in supernova, like the mixing link theory, but also moving to what the engineering community and turbulence engineering community, Division of Fluid Dynamics at APS, go to one of their meetings, what they're using for subgrid models for Reynolds average, Navier-Stokes models for studying convection. And that's something that there's a lot of interesting results going on, and we can use their understanding of convection, where they've done many, many experiments, many studies, and actually apply it to what we're studying in our models. So there's a lot of interesting physics going on there as well. And then finally, the ejector remnants. This is the focus of the meeting. I realize I'm down to like 3 minutes in my talk. This is where I think it gets exciting. There's a lot of information there. And so I unfortunately left it to the end. I'm going to have to, go through this quickly, but there's a lot of great information that we can get. Studying the relative yields tells us a lot of information. So I get excited. We'll see what Danny is willing to show us from JWST during this meeting, but there's a lot of interesting results coming out, and that's going to really change what we're doing. And I'll just stop here with the future, which is, we need to work together to tie all these observations together, but it's not just that we have a lot of great observations now, but we have good prospects for the future. And I think this is a good time for this community to really work together and do nice results. And I'll stop there. And I apologize for taking so long.
Thank you, Chris. Let's see if we have any questions online.
Yeah, so Noam, I see Noam's question. Do you want me to respond to it?
Go ahead. Yeah.
So Noam, I think that's a really good question. How can we constrain, some kind of asymmetric explosion bursting out versus this jitter jet model? That's the thing. That's one of the studies we need to do, is say, what are the features differently? And I think it's not going to be one shock breakout event is going to be able to distinguish. I think we're going to need a population of shock breakout events. This is why it's important to get a lot more data so that we can really start to distinguish. Because I think it's going to be hard for a single event, but if we had a whole population, I would guess the distribution of properties will be different between your jitter jet explosion versus an asymmetric explosion. But that study has not been done. So these are the kinds of studies we need to do.
Okay, Zhang-Yi has a question.
Yes, once you reach to nebula phase and mixing occurs, and at the same time it'll have molecular formation and dust formation, and especially it's very interesting to find out what's the mixing in the molecular level. Is there any plan you can extend your work to get the near infrared spectra and the JWST mid infrared spectrum?
So I will tell you that I am working with a team on trying to do exactly that. But we had an interesting talk on dust earlier today in the morning session, and I think there's a lot we have to study. There's a lot more that we have to do that. But I think that's a very exciting thing to be doing. And I will tell you, any single study that I've seen, there, we're still building the pieces together to try to do that. And I think it's an important piece of evidence. But someone can tell me maybe there's beyond the talks we've already seen, on the talk we saw earlier today on dust. I don't know where how many great studies have been done that do everything we want to do for this, but there's certainly people working on this to build up some nice observational prospects for this.
Yeah, we observed the Gemini spectra for near infrared. Clearly type 2 have CO formation after 100 days, a little later, but type 1 and 1B and 1C has early CO formation start from day 60. So it's apparently, those cooling and the level of mixing is very different.
Excellent. I'm going to go look at your papers now. So this is really exciting. I mean, I think this is the whole point. There's lots of exciting data we could be using to help us understand.
Okay, and Dan Milosavich has a question here.
Chris, wonderful talk. Thank you. You mentioned neutrinos and you mentioned shock breakout. So I'm one of the members of the Supernova early warning system, and I'm in charge of the follow-up response. And I'm making it a priority to find the timing of when shock breakout happens, so that we have that exact timing from when the neutrino burst happens to when shock breakout occurs. Now tell me, I've been leading everybody to believe that there's incredible rich information, because we've never had that before. With 87A, we had when the neutrino burst happened, but we didn't know when shock breakout happened. With other cases, we had shock breakout, but we don't know the neutrino burst. So can you reassure me that we'll have worthwhile constraining information with that timing, or will it be a muddled mess?
So the timing is maybe one of the easier things to get, right? We have some, except that we don't know the radius of the star. You have a supernova go off. I don't know the radius of the star, but the timing is just what's the motion of the shock through the star. So if you have a rough idea of I don't know if we're going to get from the neutrinos, what's the energetics of the explosion well enough to know what that timing will be. But I will tell you, if I were, you can get the rough estimates of the timing just by standard supernova engine is this. We know that this is, say, either a Wolf-Rayet star or a red supergiant, and that gives us rough numbers. The point is, you have to get on it quickly and be there then, because
that's what I'm trying to prioritize. We can talk afterwards, but that's what I'm trying to provide, a real number, not an estimate, and see if that's constrained.
Yeah, I mean, we can get numbers, but I tell you, the biggest uncertainty there is going to be what's the radius of the star.
Maybe with a nearby star, we can get that radius more easy. Anyway,
that's right. Yeah. Okay. So there you have a point. If you can quickly go find out what you think the progenitor was, you got the neutrino signal, and then you go frantic and you go, okay, we must have an observation of the star, and get that observation of the star and get the radius predicted, then you can get a really good number. But the question is, how quickly can you go from I found where it's located, and I'm gonna go try and pick which star I think exploded. So that will be the hard part, is if you don't know the star, you will have some uncertainty there.
Okay, so I see that Rafe has raised his hand, but Rafe, I don't know if we can maybe continue this conversation on Slack. So in the
just a quick follow-up to what was just said. It's not just the radius of the star, it's the entire structure of the star, because the structure of the star slows the explosion down. So it's not as simple as just the radius, right, Chris?
Yeah, I mean, so I was just, the radii of star, I think, are uncertain to much, the velocity I trust into factors of a few. The radius of the star, I'm not so sure I trust them that well. So it's where do you think the biggest uncertainty is? But I think that's right. What you're saying is right. We have to do how is the velocity, both what is the velocity of the explosion initially, and then how is it affected as it goes through the star? But then what is the radius of the star? And that's what we need to get exact timing.
Excellent. All right, let's thank Chris again. And thank you, Chris, for that very interesting and thorough talk on all of the issues that we're dealing with. And our talk will be a contributed talk by Michael Gabler, University of Valencia. He will be discussing 3D long-time simulations of supernova. Michael, whenever you're ready.
Okay, thank you very much for giving me the chance to talk about the work we are doing. This I started some time ago in Garching with Thomas Janke and Anno Wong-Matanarat, and now I have a student also working on this, who is Beatrice Giudici in Valencia. And I want to somehow also thank Chris for his nice introduction talk to the theoretical modeling of supernova. And I would like to highlight a bit how I see the different phases from my point of view. So first of all, we have the shock revival in the supernova, which I will not talk too much in this talk about because there's a lot of details which we don't understand too well. But then I will discuss a little bit more about the different phases which follow later, which is the expansion through the progenitor and the late time inflation to the radioactive beta decay of mainly nickel 56. And then later phases, which we in the future also would like to understand a little bit better from the modeling, is the early cooling. We have heard about a lot of this from the point of observations, but there has not been too much modeling yet of these phases. And of course, the latest phase of interaction with the circumstellar medium. We will hear a lot about this in different talks, also in this meeting. So I will not talk about this. Okay. So, So what can we learn from the first phase? Just for very short summary, as you have already heard, that we want to know a lot more about the engine of the supernova. And something we can learn from the very first phase is to look at the compact remnant, for example. We can also look at the kicks of neutron stars or the neutron star spins. And this is all depending more or less on the initial phase, where you have all the different mixing processes. You have this convection of the explosion, talking about the neutrino-driven mechanism here. And looking at the remainder, the compact remnant, we can learn something about this also. And of course, also the first phase of the explosion is very important to understand where the different ejecta are emitted to which direction, which elements are ejected. And this is something which we will observe also in the later phases in the supernova remnant, where we have the different distributions of the different elements. And what happens now if we have now the evolution of the shock and the ejector and the progenitor? All these different asymmetries will be shaped by different instabilities. And we are talking here mainly about the Rayleigh-Taylor instabilities, which happen mainly at the interfaces between different shells of the progenitor. So we can see here, for example, on the plots on the right side, where we have different measurements for the different instabilities, which are given by this factor here. And we will see that in different phases, we have different phases of Rayleigh-Taylor instabilities. And also we will have different shocks forming at the shell interfaces mainly. Now, how this looks in some nice figures, in some 3D models, you can see here. This is at the beginning of the long time evolution. This is just after the explosion onset, which is roughly between 1 and 2 seconds after the explosion. We see here nicely the different bubbles and initial plumes, which are caused by the convective instabilities during the onset of the explosion. And we see that these at this point that these plumes will expand. Now they expand into the progenitor of the star, and there they will interact, and they will be subject to the Rayleigh-Taylor instabilities. These instabilities make that these big initial plumes, they fragment into some smaller, small-scalar structures, and they start to form some Rayleigh-Taylor-like fingers, which are very typical for this kind of instabilities. Now, waiting a bit longer, now we have about 1,000 seconds for this particular model. We see now that the reverse shock forms, which is coming from one of the interfaces. We see this very nicely here in this reddish, almost spherical shell in the plots. And we will see how this shock now will start to compress the innermost ejector and let only some of the Rayleigh-Taylor fingers stick out, as we can see here, for example. Now we see very clearly in the second phase of Rayleigh-Taylor instability that these initial strongly or much larger scale plumes fragment into these very elongated fingers, and the central part of the ejector is compressed to an almost spherical configuration. Now, if you go to the second phase, where you now have the inflation due to the beta decay, we will see how these fingers will inflate. And for this, we compare in this plot, for example, the volume of the nickel-rich surfaces, which I was just showing in the plot before, how they would behave with and without nickel decay. And for this, we can look at this line here. We see some initial compression of the volume of these fingers, which is rescaled here by the time, just to allow for comparison at different times. We see that without nickel decay, after a while we would reach homologous expansion. This means the volume wouldn't change. These rescaled volume wouldn't change with time. However, now due to the nickel decay, these structures will inflate again, and this is just a small measure for this. And we see that all the models we are investigating here, we have like 4 different models with 3 different prescriptions of the beta decay here. We see that after roughly, so that depending on the model, the blue supergiants, which are more compact, they start to, they initially start to decrease this rescaled volume up to about 1 day, then increase the volume up to about 100 days, and then stay more or less constant. And similar things happen to the 2 red supergiants, which we have here in the set of models. They decrease the rescaled volume of these nickel fingers. This is the interaction with the reverse shock. That's why they are decreasing. And then at later phases, they start to increase until about 100 days or maybe 1 year. At this time, the effect of the nickel decay is not so strong anymore. And we can assume if there's no interaction with some other shocks or something, we are in homologous expansion. So how this reproduces in these plots, we have seen before. We just I discussed the 4 plots on the top before. And now here we see what happens roughly at 1 day. We see that the nickel fingers, they stick out much more. The central region is very compactified. It's very central. And then the nickel decay sets in. They have a lot of nickel. The clumps will inflate more. The fingers will expand more. And we see that these clumps, which were initially separated, they start to merge again. And we also see that the central bubble also expands much more compared to the rest of the system. Altogether, one can say that also sees that the initial plumes, which are here roughly, they are still represented by these final finger structures. So we see really a relation between the final structures, which are then observable in the remnant, can draw conclusions how the initial asymmetry have been seeded during the first second of the explosion. How this looks for one of the models, I hope you can see here. Okay, obviously the video doesn't work how it should. Okay, then let's just compare the different structures for the models we have simulated. So for some of the models we have simulated, where we have 2 blue supergiants on the red and 2 red supergiants on the white side. And we see that the models look very different. Depending on the progenitor, you can get really different results in the morphology of the ejector. And this is now only the nickel-rich ejector. Other elements will look also different for even a given model. So for example, for this model B15, which is very prone to Rayleigh-Taylor instabilities, we see a lot of fingers in very different directions. While in contrast, the other blue supergiant here, the model N20 of our set, is still very spherical. Because in this model, there was no time for the Rayleigh-Taylor instabilities to grow. So all the matter is almost distributed spherical. For the 2 red supergiants here, we see some preferred directions where we had some initial asymmetries in some preferred directions, which we now see also in the late phases, which are very well, which look very characteristic for the model. But how exactly these fingers stick out is a stochastic process. This depends on the instabilities during the explosion itself. Okay, let's see this video. Video also doesn't work, probably. Okay, that's not a problem because we see here the final outcome of this. This is now a density slice of the model. This is also, again, the model B15 I was discussing before. What we see here very nicely is now that the initially overdense structures, where you had initially, due to the explosion mechanism, you had the nickel-rich fingers, which were overdense with respect to the surrounding medium. Now, at the end of the simulations, which is now about 1 year, we see that these structures are more or less hollow if you compare it with the surroundings. You see density contrast of a factor of 10, depending on how strong the beta decay is, up to a factor of 50 between the center of these nickel-rich fingers and the plumes and the walls in between the different fingers. So you really see that the structure changes due to the beta decay here. And this is also something we observe, for example, in CAS A, where we have these bubble-like structure, and this is very nicely represented here in these kind of models. Now, what we can do next is simply compare, or what we have done already some years ago, is compare these models. This is the 4 models I have discussed before. Now compare to observations of 87A, and just by looking at these very simplified comparison, which is more or less qualitative, we can already see, for example, that for the CO observed in 87A, that some of the models they don't work. So the radius of these of this ring, which is just a slice in the density of carbon and oxygen from the model, is much too large to be able to explain the structure we observe in the observations. Also, the number of clumps and the size of the clumps is very different from the observations. So this model would not be able to explain the observations, just to show an example. But of course, this is a very qualitative approach to compare now the 3D data and the 3D observations. And the next step, which is, I think, is very necessary at this point, that we need to understand this more in a qualitative way. And this is something we need to address in the near future. So with that, I want to conclude. So I want to highlight again that the asymmetries which we observe in the end, they are already seeded during the explosion. So we can really make a connection to the very first moments of the explosion. Also, the propagation, the asymmetries are then, or the ejector are then shaped through the propagations to the progenitor and through the beta decay in a way that that the structures inflate, and they are accelerated mainly by the 2 processes, by the instabilities in the beta decay, that we can get accelerations of the material by 100 to 350 kilometers, for example. What we observe nicely in the simulation is the density enhancements between the nickel-rich bubbles, and these bubbles become then underdense compared to the surroundings. And of course, we can now do also with the simulation, we can start to do some first quantitative analysis. We can make some statistics on the clumps, how many clumps are there, how big are they, what is the separation between them. We can look at the spherical harmonic decomposition. And I think I don't need to convince anybody here that it's now a very interesting time and exciting time to compare the simulations to the observations. But for this, I also think we still need to work a little bit how we can quantitatively compare the observations. And also, we have to do something on the simulation side. We also need more simulations to be able to say something quantitatively. Now we have a set of models. We have some more blue supergiants. My student is now working also on the red supergiants. So we need to build up a library of models which we compare to observations to learn something about the dependence on the progenitor, on the stochasticity of the explosion, and things like this. And I just want to end the talk with some advertisement of a workshop I'm organizing in Valencia in about 3 weeks. So I just extended the deadline for registration. If anybody is interested, also will be kind of a hybrid meeting. So nobody needs to travel to Europe. I guess it's not very easy on a short time like this, but I would be happy to welcome some of you. Okay, thank you very much.
Some of us?
Yeah. Everybody, but I guess not everybody can join.
We have a Q&A on the thing. Might have missed this, but what was the shock breakout timescale on the B15 model? And can the Rayleigh Taylor finger create a highly oblique shock as it breaks out of the star?
So we hadn't looked into how oblique the shocks are, but well, I think the shock is not so affected as the Rayleigh Taylor fingers, because the shock is further outside. So the shock is not looking as asymmetric as the fingers themselves. That's one issue. And the timescale for the blue supergiant, I think this was the timescale. You can see it. The timescale was like, I think, was between roughly around these 7,000 seconds here. I think this plot was roughly shortly before the shock breakout. if I remember correctly.
And actually, I'm gonna go behind you to
Yeah. Thank you, Michael, for very fast. Did I understand correctly, in one of your first slides, you showed how the, time scale, and how the scale of volumes of the bubble
Yeah.
change or surface area. Yeah, and I think you mentioned, that, these family of V15 models, for
Yeah.
example, differ by how the beta decay is modeled.
Yes.
How does it differ? And it's quite
So
a big effect.
yeah, so the issue is like in our simulations, we have a simplified network for the calculation of the nucleosynthesis. So we have a tracer where we put in some of the
Go ahead.
some of the heavy elements. So for example, so first of all, one version was without beta decay, which is the wet curve here. So you don't see any inflation. And then the model, which is calculated by our network and also by our neutrino transport. Our neutrino transport was simplified here. So we don't get all the details of the alpha bridge freeze out very nicely reproduced in our simulations. So what we know, if compared to more sophisticated simulations, is that the truth or the true value lies in between the blue curve and the black curve here. So we need to take roughly 50% of a tracer, where we put all the heavy elements in, and to treat it like it was some nickel 56. So the truth should be lying between the blue and the black curve here. That's a more realistic value.
hold on, we'll take that question.
There's three modes of failure that can happen with your code that essentially makes them things that don't look like observations. One of the modes of failure is physics in the code is wrong. The other mode of failure is the sort of underlying scenario of models wrong. The third mode of failure is like the specific realization of the model that you're using is wrong. And so I'm wondering, when you're sort of talking about metrics of comparing data to model weighting. So I think if you choose these kind of wavelet models or other models, I'm wondering which mode of failure are you testing? You know what I mean? Like, does a wavelet tally if the code, the physics, the underlying physics of the code is wrong? Does it tally if the realization is wrong? Or when you're measuring bubbles?
I'm not sure if I understand, especially the last point, the last kind of.
So essentially, when you're trying to compare and you're saying, okay, there's more there's more bubbles from one on simulation versus the observation. Does this tell you if the physics of the code is wrong, or does this tell you if the specific realization of this simulation is wrong?
It's hard to say. I would say
I
it's
think
hard to
that's an
say.
important question
The
for
issue is
any
like,
metric.
I hope what I would like to find out is what happens if you do a couple of simulations, not only like one or two, and understand if you're looking, for example, some characteristic differences between red and blue supergiants. I think in this case, you eliminate many of the sources of the errors you're mentioning. I'm not trying to reproduce one model to one observation.
Yeah.
This doesn't make sense. One needs to do this in a statistical sense to some extent. There's a handful of models which will be able to simulate, because all of this takes a lot of time. But I don't think that we will ever be able to pin down one model to one progenitor or something like this. Especially also with all the uncertainties which are intrinsic to the processes, to the stochasticities and all of this. And independent from the problems you're saying, right?
Thank you.
I have one last question from John Slater.
I was curious about the characteristics of the clumps. I mean, can you say anything about like total densities relative to the other rest of the ejector?
Yes, we have in the paper, we have analyzed this for example, for the nickel-rich clumps. But all this depends also how you define the clump. For example, what is the density threshold for you saying that there's a clump and there's no clump? So it's a quite complicated issue. So unless we specify exactly what we are trying to compare to, it's hard to give you some numbers on that.
Just bearing on dust production, dust formation.
Yeah, that's something interesting I would like to look at the future also. When we have a bigger set of models, we understand better how this happens, also have a better understanding of the stochasticity of the explosion and stuff like this. I think that's something definitely to look into.
Okay, let's thank Michael again. Our next speaker is Tomoki Matsuoka from Kyoto University. He will be telling us about long-term evolution of a supernova remnant, posting a double neutron star binary. And this is a 15-minute contributed talk. So whenever you're ready.
Can tell you?
Yeah.
Okay. Yeah. Okay. Okay. Yeah. That's okay. Okay. So thank you very much for giving me an opportunity to have a talk in this workshop. My name is Tomoki Matsuoka. A PhD student in Kyoto University working with Herman Lee. And today I'll talk about the long-term evolution of Supernova remnant posting a double neutron star binary. So first, I'll give you a brief introduction about this study. So as you know, double neutron binary is a posterior object massive star involving the binary, and it has been observed. It has been observed by radio wavelengths, and I can't see the console. So then that's okay. Okay, so the double neutron binary has been observed in the radio wavelengths which probe the orbital decay of the orbital decay to and which stresses which shows the validity of the general relativity. In addition, in 2017, Lyman collaboration has succeeded in detecting a gravitational wave and the associated optical counterpart called kilonova. So much attention has been paid to this object, and one general issue is how the formation process of the double neutron binary. How are they formed? Naive question, naive answer is that making it 2 times of Hawk's supernova. So there is recently the scenario recently proposed is called the ultra supernova scenario. Actually, there is a problem that if the ejector mass is larger than the total mass of the binary, then the binary becomes unstable and dynamically disruptive. So in order to avoid such an unstable situation, the ejector mass should be small. So therefore, in the process of the stellar evolution, the mass loss from the supernova progenitor is inevitable. So in this scenario, two kind of the mass loss mechanism is considered. First is the common interaction, which can reduce which can eject the hydrogen envelope in the secondary star into the interstellar space. And in addition, this scenario considers the Roslow overflow. And this mechanism can strip the helium layer of the secondary star away. And then after the secondary star evolved into the carbon-10 star with two solar masses also. And if such a star explodes, then we can observe such a star explosion as an ultra supernova, and the ejector mass is 0.1 solar mass also. This scenario can realize a small ejector mass and avoid the disruption of the binary systems. Recently, the observational examination of the validity of the USSN scenario has been conducted. For example, optical radiations from this explosion has been predicted by some studies, and thanks to such a model recently the candidate for the USSN has been discovered, which is called IPTX14 PQR. And in addition, X-ray or radio. In addition, the radiation from of the X-ray and radio wavelengths has also been investigated, And today's topic is the supernova remnants regarding this object. If the USSN has evolved for a long period of time, then we can expect that such object will be observed as a supernova remnant hosting a double-net binary shown in this figure. So here we call such object as a ultra-specific supernova remnant USSNR. So we can expect that such object can also examine the validity of the USSN scenario, but so far we do not detect any kind of such object. So we need to know what is the property of USSNR and how the evolution of such object is characterized. So one key physical process is the circumstellar medium CSM and USSN progenitors. Actually, the binary system we experience two kinds of binary interactions. There should be a peculiar CSM around the progenitors. One is the common. And at first, the progenitor we explain the common interactions and the ejected hydrogen material will distribute in the outermost layer of the CSM. In the inner region, in the next stage, then the progenitor experiences the Roche-Lobe overflow, and actually the helium gas stripped away by the Roche-Lobe overflow will first stream toward the companion neutron star. However, the stellar evolution model predicts that the accretion rate of this Roche-Lobe overflow is order of 10 to 5 solar mass per year, or so 50 orders of magnitude rather than the Eddington limits. Therefore, we can expect that the transfer gas should escape the binary system and which leads the formation of the circumstellar medium. And a supernova ejector will collide with the circumstellar medium from the inner region of the system. So as you can see, that the ejector mass is smaller than the total mass of the circumstellar medium, and we can expect that the CSM will plays an important role, essential role in characterizing the USSNR properties. So we need to pay attention to such a features. So here I briefly show you the procedure of numerical modeling. First, we prepare the initial set of the circumstellar medium formed by the common envelope interaction. So we prepare the initial set of something like this, which describes the common envelope component smoothly connected to the interstellar medium. Today we do not go into detail about the difference of the initial profiles, but anyway, we prepare something like this. Next, we demonstrate the mass loss from the progenitor binary by calculating the hydrodynamics of the stellar winds, something like this. And then we can obtain the profile of the circumstellar medium. By using this profile, next we investigate the properties of the blast rate in this SNR, and we can obtain the information about the blast rate and the density profiles. By using such information, we can calculate the radial luminosity and so on. Today and so on. Okay, so here we show you the result of our calculations. First is the reproduced CSM. This figure shows the density and temperature structure of the CSM. And as for the density structure, we can see that the non-uniform density distribution is realized fitted apart from the distribution proportion to R-2. And in addition, as for the temperature structure, we can see that there is a hot plasma whose temperature is up to 10 to 8 Kelvin or so, and so 10 to 8 Kelvin. And the location of the hot plasma is in the vicinity of the isolation cavity or around 4 parsecs or so. Around 4 parsecs or so. So we can say that there is a complicated structure of the CSM in the USSNR. So we need to consider such an effect. So next we show the time evolution of the blast wave. The orange line in the left here shows the time evolution of the velocity of the blast wave, and blue dashed line shows the maximum of the blast wave. And we can see that there is a two timing at which the blast wave is accelerating. These timing are corresponding to the rotation where the CSM density is rapidly decreasing. So this is physical. This is physical, and this can be naturally explained. However, we can see that the blast wave is rapidly decreasing at 300 years, and the Mach number is also decreasing down to order of unity. What occurring is the interaction between the blast wave with the hot plasma shown in the right figure. This figure shows the temperature structure, and as the temperature is 10 to 8 Kelvin or so, then the sonic velocity is 10 to 3 km per second and km per second. So as the blast wave collides with such a plasma, then the Mach number becomes the order of unity. Therefore, we can observe that the blast wave is disappearing at the collision with the hot plasma. We suggest that such a feature is one of the unique characteristics of the USSNRs. Next, we show the observable radio light curve of this object. This shows the light curve of radio luminosity comparing with the some type 2N supernovae and galactic SNRs. And this red line shows the detection rate of the previous survey, assuming that the object is rotated 10 kpsec or so. And we can see that the radio emission from USSNR can be bright enough to be detected if our USSNR inhabits in our galaxies. And however, we can see that the luminosity is fainter than some type 2N supernovae and galactic SNRs. This is one conclusion. And in addition, I have mentioned that the blast wave is disappearing around 300 years or so. However, the radio luminosity continues to be bright even after that. What occurs is that electrons accelerating in the pulse has potential to produce radio emissions. So be energetic. Therefore, even after the death of the blast wave, then the electron can be energetic, and we can be energetic, and even after that, the radio luminosity can be bright, decaying with the adiabatic cooling. And finally, we show the evolution of surface brightness of this object. The right figure shows the sigma deviations diagram, and the surface brightness as a function of the diameter of the USSNR, comparing with the galactic SNRs. And we can see that the surface brightness is fainter than the galactic SNRs, and while the diameter of the USSNR is the order of 10% or so. So therefore, we suggest that the characteristics of USSNR, therefore we suggest that these 2 points can be also characteristics of the USSNR. Okay, so here is a summary of today's talk. We have investigated the long-term evolution of supernova remnants causing a down emission. Finally, and especially paying attention to the role of the detailed structure, more formed by the supernova physics modeled by the mass loss activity from supernova progenitor. And we show that inhomogeneous CSM structure is realized in this object, and it is characterized by the activity of the loss overflow. And finally, we suggest the nature of the USSNR as follows. One is the disappearing blast wave, second one is the faint radio luminosity, and third one is the faint surface brightness for its typical diameter. That's all. Thank you very much.
Do we have any questions?
We have one in the Q&A.
Okay. So Noam says that he expects that CSM be highly non-spherical and possibly very bipolar, to the degree that the aspherical ejector CSM interaction is not accurate. Therefore, the ejector expand freely on the poles, etc. Do you have any comment about that?
Actually, for it is important to consider the asperity in this system, and we expect that the material ejected by through the common interaction will distribute in the equilibrium plane, and in a polar direction, we expect that there in the polar direction there distributes interstellar medium. So depending on the state of the interstellar medium, the asperity will develop to some extent. So yes.
Good point. Thank you. Evo?
Okay, thanks for your great talk. And I may have missed this. How many USSNRs do you expect to be observable in the galaxy right now based on the population?
I see. So
and their lifetime.
actually, we have estimated the population of the USSNR in a galaxy, and by considering the time, by considering the time scale of the observable with the divided by the birth rate of the USSNR, and we have estimated that the population is the order of unity. So it is actually it is severe to detect such an object, but if we can increase the number of the detected SNRs, probably one of them may be USSNR.
Okay. Let's thank our speaker again. And I'd like to say that our next talk is our last one of this session. It's Ray Fix, modeling core collapse supernova from core collapse to shock breakout. It's 15 minutes, contributed talk. And when you're ready, when you're set up, you can get started. So.
You guys hear me and see everything?
Yeah, perfect. Thank you.
All right, very good. It's always good to be the talk to fans between everyone and lunch. It's always fun. I'm glad you guys will pay attention. I'm sure you're not thinking about where you're going to go. So I wanted to update you guys on some things that we've been doing in the last couple of years to try to bridge the gap between the current models that we've been doing with our code Chimera, which basically end after the shock has been fully revived, and the actual supernova that happens hours later, right? And there's a bunch of motivations for this. One of the motivations for this is frankly jealousy of the type 1A guys, since when they do a mechanism model, they're done when they get done and they can hand it off to the observers right away. And instead, we've got 10 or 20 solar masses of hydrogen between us and the thing we want to observe. Right? Another motivation for this is this whole idea of multi-messenger astronomy is kind of a farce unless you actually have a string of models that connects all of the observations together. If you care about the neutrino and the gravitational wave observations at the very beginning during the formation of the neutron star and the initial powering up of the shock, and you also care about all the optical observations that are going to happen hours, days, years later, you have to have a string of models that connects them, because otherwise you're not really looking at all the messengers for the same event. Right? So that's what we set out to do. And by we, mostly I mean Michael Sandoval, who graduated last summer. This is mostly his dissertation work. So all the good stuff is his and all the mistakes are mine, of course. So real quick, we've heard a lot about inhomogeneities in supernova remnants. We also know about inhomogeneities in supernovae. The Bochum event is a classic example from 87A. There must be 10 to the -3 solar masses of nickel way out in the hydrogen envelope. How did that happen? How did it get there? That's the kind of process that motivated a whole lot of simulation work early into the 90s. Obviously, with supernova remnants, you get detailed views. You actually get imagery. You can see asymmetries. You can see asymmetries between different species. All of this has to have a root cause coming back to the explosion, although obviously that gets mediated by the passage through the star, the passage through the interstellar medium, etc. So we need a series of models that run through all of these things. it's been 30 years now, and Chris and I were both around then. I don't know about, and most of the rest of you weren't, but we were both around when they started doing this modeling with multi-dimensional models with neutrino transport in them. Part of the motivation for doing that was that the earliest models of multi-D for progress to the star didn't produce the kind of velocities that you need to match observations. So there was evidence going back now 30 years that we must have asymmetries contributing from the very beginning, right? And so this is the process, right? And so Michael Gabler talked to some of it about this, but let me emphasize this again, because I think it's important. Once you launch the explosion, you're not done yet. You still have to understand the structure of the star. And in some ways, it makes it much harder to make a mapping between what happened in the very first few seconds and what you're going to see after a day. So this is some of the famous work, earliest work that was done on this by Kifanides, Plewa, and collaborators. The key thing I want you to see is, first of all, look at how the density progresses in time, and you see features develop on the left as you pass different interfaces and such. The figure on the right is what the shock velocity looks like as a function of radius as it moves out. And it is entirely determined by the initial velocity of the shock, i.e. what the mechanism set it to be. And then the continued evolution as it passes through these different layers of the star, mediated primarily by this rho r cube measure, where the gradients of rho r cube are also gradients in the velocity, the acceleration. So when the log rho RQ is increasing, the velocity is decreasing. When you reach places near shell interfaces where this drops, then the velocity increases. To go back to the question that was asked to Chris about how do I know what the timing is for the difference between the neutrinos and shock breakout? Well, it's the integral of that V shock curve as you move all the way through. And it depends on the progenitor. It depends a lot on the progenitor structure, as well as on the mechanism itself. So there's been a good amount of work done primarily by the Garkin group, and Michael Gabler already showed us some of these results, and he's part of that effort. And really nobody else in the field has been doing very much of this, which is a big problem. But the story that these two sets of plots tell you, one is essentially, the top plot is essentially the distribution of nickel-rich material colored by velocity at the end of the explosion developing. And then the bottom panels are the same models, one-for-one matching with the story at essentially shock breakout, 50 to 60,000 seconds later. And so the difference between these two sets of images is all about a race. It's a race between the shock and the metal-rich ejecta, and then throwing into it a third piece of the puzzle, which is the reverse shock, right? So as the shock moves out, it's accelerated and decelerated as it goes through the envelope. The metal-rich bullets are trying to keep up with the ejecta, and it matters that they keep up with the shock. It matters that they keep up with the shock because of the reverse shocks. When the reverse shocks get launched, as you hit shell interfaces, depending on the strength of the shell interface, this reverse shock may be weak or strong. That's going to suppress the material coming behind it, unless you're close enough to the shock that you don't get affected by the reverse shock. And so the story of the image on the bottom left is that that's essentially what happened, that the bullets manage to stay close enough to the shock that they propagate all the way out and stay as bullets, and the rest of them get mashed. Right? So this is the context of what's been done before, and Michael talked a lot about this a few moments ago. We set out to do this a little bit better by using the best supernova model we could get. Most of the work that's been done in this area has been done with somewhat approximate supernova models, usually gray neutrino transport models, with some parameterization. So we set out to basically say, this is a Chimera model. What does it look like at the end of the day when it hits the surface of the star? So in this terms, Chimera is fairly sophisticated neutrino transport code, of high relevance to what I'm going to talk about in just a minute. It's a spectral neutrino transport code. So we do very expensive neutrino transport, but we do very accurate neutrino transport, which is important for understanding the composition of the material. In the particular model that I'm going to talk about, we also have a large nuclear reaction network, 160 species, from protons and neutrons all the way up to zinc and germanium, something that is also not usually done in supernova models. Usually they suffice with an alpha network or even less. But we had the capability, and we thought that we had a good test for it. So the test we picked for it was this D9.6 model. D is our designation for the version of Chimera that it is. 9.6 is the progenitor map. This is the model from Hager. where Alex was trying to produce a very, very light iron core. What you see on the right is essentially the last couple hundred milliseconds of the evolution in entropy for most of the image, and then in YE on the left, the electron fraction. And so this is the structure that results from this model. It's a very, very light iron core. It therefore has a somewhat different supernova mechanism than the standard mechanism, because the shock doesn't really stall. It slows down, but then it reaches the edge of the iron core and encounters a very steep gradient in density, because this is a light iron core. And so it then accelerates down that gradient. And so neutrino heating does happen, but it's not essential for the movement of the shock initially. So as a result, you end up with this very different kind of supernova, where I have relatively, so the red is the shock wave moving out. I have behind it relatively low entropy material, which has relatively high neutron richness. You can see neutron richness is of even 0.4. And then behind that, I have the neutrino-driven wind and the hot bubble, the traditional hot bubble, where I have high entropies and material that's now proton-rich. And so this results in kind of unusual ejecta. This is not a normal supernovae, but you'll also notice the explosion is fairly spherical, but the ejecta trailing behind it is not. So if we want to talk about completing our Chimera model, we need to make sure that we're done with the physics that's essential to Chimera. So essentially for this question is, are we done with the neutrino heating? And so the neutrino heating, for the explosion energy for this particular model is shown in the green. The solid line is the 3D model. And you can see that the explosion energy has leveled off. It's not completely asymptotic. In an ideal world, we would have run this a little further before we moved it over into Flash, but allocations don't allow for ideal worlds. But you can also tell from this graph why of all these models we had the same epoch, we picked this one because it's the only one that was anywhere near flat. So hence we picked an unusual model for our first test. Another important test is to look at whether the nucleosynthesis is done. And so what you can see in this image at the right is that the nucleosynthesis processes are largely done. If you have a sharp eye, you'll notice that helium and carbon, for example, are still climbing at the end, but they're not climbing because nucleosynthesis is happening. We're not making helium and carbon. We are instead liberating helium and carbon, because this image shows material that's unbound, material that we think will be part of the ejecta. And so you can see the two-phase production of nickel 56. There's an initial phase, which is explosive silicon burning from the shock. And then there's the second phase, which is the neutrino heated material being ejected. So this is alpha-rich freeze-out, and they come in roughly comparable amounts. The titanium-44 only really comes with the alpha-rich freeze-out material, not so much with the explosive silicon burning material. And you can also see some other interesting things here. There's the neutron-rich material highlighted by calcium-48, and we'll talk some more about that in just a second. So I think on the basis of this, you can say that the model is pretty much done. One interesting thing that comes out of the results of this model is that there's a very interesting nucleosynthesis of nickel that happens. And this is because of the kind of multi-phase process where I have initially neutron-rich material being ejected relatively unheated and being followed up by material that's been progressively more and more heated over time. The result of that is progressively more and more changes to the YE. So if you'll notice that the very first things to rise and join the ejecta on this curve are the most neutron-rich species like nickel 64, nickel 62, and then gradually over time I get contributions from more and more neutron poor material. And you'll notice quite interestingly that there's actually more nickel 60 produced in this model than nickel 56. Not a normal thing for a supernova, but probably a very normal thing for an electron capture supernova, for one of these oxygen neon collapses, which end up being very similar to these lightest iron cores. So just for fun, here is a cutout of the nickel 56 versus nickel 60 species, and because of this staged production of species, you end up with a pattern matching cutout. Right, I can see there's a little bit of nickel 56 that actually reaches out to higher radii. That's the nickel 56 that comes from the initial shock burning. And then there's a wave of nickel 60 that follows, and then there's this wind of nickel 56 that follows behind it. And so that's going to affect everything that comes later. So that's our Chimera model. At 466 milliseconds, we mapped this over into Flash. We chose Flash because it could still do nuclear reaction networks, including the same 160 species network that we had done before. But it also had AMR. Unfortunately, it turns out that we couldn't use AMR with the gridding that we ended up with, so instead it's a monogrid. You can look at the details of the resolutions, but roughly speaking, this is comparable or somewhat better to the resolutions that of the competing efforts. And there's the image on the right of what it looks like as it starts in flash. So here is our version of this velocity and rho r cube plot for the model. The dark blue line is the mean shock velocity, and so you can see it declines as it goes through the star. It's decelerated. There's one small episode of acceleration at the helium-hydrogen interface. What we've also added on here, though, is the dotted line. The dotted blue line is the highest velocity of the bullets. And so in our particular model, the bullets are actually keeping up with, and in some cases, pushing on the shock. And so we're going to end up with a morphology that reflects that. That's very different from what previous models for this progenitor that were done by the Garking folks had done. This is the model by Stockinger et al. 2020, where they don't see this kind of bullets keeping up with the shock. We have a couple other models on here that are basically the code 3D. 3D means it was a 3D Chimera model that was followed up with 3D in Flash. The 2D, 3D models were a couple attempts at trying to take a 2D Chimera model and see what it would look like in 3D. And it actually turned out whether or not we aligned it with the grid of the Flash model or not. And I can talk about that if somebody wants to. It's talked about in detail in the paper. So here is 3 separate images of the shape of the nickel surface at 3 different epochs. One is the beginning of the flash simulation, one is about 200 seconds later, and one is at the end of our simulation, or near the end of our simulation. And so what you can see is that the bulges in the nickel distribution at the very earliest times manifest themselves in the middle plot as the growth of mushrooms. When the nickel and the shock get to the helium carbon oxygen interface, that's Rayleigh-Taylor unstable, and you get the generation of mushrooms. But you'll notice you get the generation of mushrooms everywhere on the surface. The larger mushrooms, of course, are the ones that started first. They've grown the most, and that turns out to be very important because once you get hit by the reverse shock, most of those mushrooms get crushed, and the end result is the image on the right after several more generations of shock passage, where only a handful of the largest mushrooms end up as plumes. And most of the material has been largely spherized. So this looks similar to, or kind of intermediate to, the 2 different cases that I showed you from the previous work that the Garking guys had done. For fun, here is the distribution. This is an isosurface drawing of carbon in green, helium in blue, and nickel in red, although we've chosen nickel 60 instead of the traditional nickel 56. A, because we know what the nickel 60 composition is, and B, because it actually makes a difference in this model. So this is just a 3D rotation of it, so you can get all the perspectives of it. But what you get is nickel bubbles above a relatively spherical heavy element composition. And the nickel bubbles are swaddled in helium. So another view of that same transformation, the image on the left is 3 colors: silicon, nickel 60 in green, and nickel 56 in red, and that's the initial distribution. You can see coming out of the Chimera model that there's this layer of nickel 60 sitting on top of our nickel 56. And that turns out to be important as the elements move through the model, because the nickel 60 stays ahead. It's the nickel 60 that keeps up with the shock. It's the nickel 60 that populates the bullets with a few exceptions, whereas we have a much more spherical distribution of nickel 56. Again, this is an unusual supernova, as more representative, I think, of the oxygen neon collapses, the ECSN, than a normal CCSN. But nonetheless, it's an interesting example of how the details matter in this. A couple more quick slides before I'm done. This is an image that shows the composition of essentially a crosscut across some of these bullets at constant radius. And so what you can see is the nickel bullet, right? So it's nickel because it's got of order a few percent, maybe 10% nickel. The orange lines at the top is mostly actually helium. There's a good amount of oxygen, lesser amounts of silicon, right? So this is a very mixed compositional bullet. This was an education for me. I'd always kind of thought of nickel bullets as being essentially 100% nickel, but in fact, they're relatively light in nickel. They're mostly helium. They have a lot of other heavy elements. But of course, as Michael was saying, the nickel matters because the nickel heating will inflate these bullets and crush out all the other material around. So here's kind of the most important thing that I want you guys to carry away from this. And so just pay attention to the images on the upper part of these 3 sets of images. One is the radial velocity distribution of the heavy elements and the light elements. The other is the mass distribution, and you can see we have heavy elements mixed all the way out, at least at a low level. Again, this is the bullets added out into the hydrogen envelope. Again, you can see the same thing in the velocity distribution with heavy elements reaching out to 2,000 kilometers per second at appreciable concentrations. So this is quite distinct from what our colleagues in Garking saw for the same progenitor, which is shown in the middle column of these two images. There's radius on the top and velocity on the top and mass on the bottom. Right? They did not, for this Z9.6 model, see the same high level of mixing out to the extremities of the star. Instead, the heavy elements are much more restricted in mass in that particular model. And in fact, our model for the Z9.6 looks much more like one of their more conventional iron core collapse models, which is shown on the right. The fundamental difference here is that our explosion energy is about a factor of 2 different than the Melson model that Stockinger used as his initial conditions. And so, yes, the structure of the star has a dramatic impact on all the things that are going on, but you can still see the impact of the mechanism in the ejecta. In this case, it's probably the error that one or both of us is making that highlights that fact, right? But you can still see dramatic differences resulting in the eventual observables from the first second of evolution. And so with that, let me go to my summary. This is a very unique supernova, this very light iron core, but we've run it all the way out because we could, because we've tried to set for ourselves now a goal of doing that for every model where we've reached an asymptotic explosion energy, so that we can genuinely talk about multi-messenger astronomy, so that we can hand this model off to folks who are interested in shock breakout and light curves, and they can then hand it off to people who are interested in remnants. And so if anybody wants to work with an entirely very detailed and very large model, please let me know. We have data. We can make some interesting things happen. The structure of the progenitor star obviously matters a lot. And as Michael said earlier, you can definitely see that in the evolution. And we see that as well, of course, in our simulation. But by the simple comparison of our model to their model for the same progenitor, we know for sure that we can see consequences of the mechanism at 19 hours later, and presumably therefore in the light curves and in the remnants themselves. And on that note, I'll stop. And I have no idea how I was on time.
I won't comment. Thank you. Let's thank Rick for that fantastic talk. And the highly detailed modeling. I can speak from experience how difficult it is to try to couple these disparate models together to try to produce a end product. So that's heroic. Do we have any questions here in the audience? We have time for exactly one question. So Dan has a question.
Sure. First, I want to say thank you for following up the shock breakout timing. Next, I think the last plot was among the most interesting for me, the yields comparison. And I know this is for a specific event, but we hear CASA a lot at the meeting. You know, Martin was presenting this result where the majority of the iron that we're seeing seems to be above 3,000 kilometers per second. And he's with no detection, at least he put constraints of less than half the solar mass of iron near the center below that. So this is speaking to some real mixing in the explosion process. Do you have any comments on that?
So for more masses, so this is a very weak explosion. The fact that it managed to mix all the way out is kind of a hit or miss thing. The reason we get it and Garking doesn't is that tenth of a beta difference matters. If you were talking about a model that had an explosion energy that was closer to a beta, all the velocities are higher, the mixing is stronger, the ejecta has more heat to it, so it has a better ability to keep up than this particular model did. But on the other hand, you know, my perspective on this is relatively simplistic. I'm trying to build a model that does the nucleosynthesis, and then I want to see what the consequences are. The kind of parameter study we need to do to say, given remnant A, what did that come from? is kind of too expensive to do the way I'm doing this, right? These are, 100,000 node hour jobs. The Chimera part, the Flash part was maybe a tenth of that. So we're never going to have the kind of, think of Alex Hager and the 500 models he computes for chemical evolution. Some level, we need to replace all of those with multi-D models to get the nucleosynthesis right. And yet, on the other hand, I don't know how the hell we're going to do it. We need to, have feedback between the most sophisticated models we can and simpler models. But that feedback has to be realistic and it has to work. And so far, it doesn't.
Okay.
Kind of answered your question, but not really.
All right, so I have to interrupt here because we have, and many people know, the CFA is isolated on an island, so getting lunch in a timely manner is something that we can't always do. And we do have a new session starting at 2 p.m. So Zhang-Yi, I encourage you to post your question in the Slack chat, so that Rafe can address it there. I'd like to thank this morning's speakers. And I welcome everybody to rejoin us again at 2 p.m. Eastern time for the afternoon session. So do you have anything you need to add? You'd like to add?
To the people connected on the Zoom, we are going to shut the Zoom down and then restart it at just before 2 p.m.
So let's thank all of our